Okay, so welcome to today's lecture on neural networks and deep learning. On Tuesday, we started to talk about convolutional neural networks, time-delayed neural networks, and recurrent neural networks. And we didn't completely finish, and that's where we want to continue today. So we discussed in detail the basic time-delayed neural network, the basic recurrent neural network, and then we highlighted a bit a challenge of recurrent neural network, that they have the ability to incorporate global context, so to really take into account all your previous inputs you have seen. However, in reality, it's really difficult to learn from these. We saw with this example. One moment. We had this example of sentiment analysis, where we have to extract the sentiment at the end of the text, and especially if this is a long text, the problem arises that our sentiment at the end depends on text which is far at the beginning. And if we want to do that with a standard neural network, recurrent neural network, the problem is, if we look at the derivations, is that we have this matrix WH, which connects to hidden states. We have it very often occurring in the derivation. So if this weight is a bit higher than 1, then we have very high gradients and we might not have good learning. If we have it a bit lower than 1, we have very low gradients, and we also can do successful learning. And this is a major challenge of RNNs in general. And there's different ways of dealing with this. And we wanted to look now today into one, which are called long short-term memory networks, short LSTMs, which I think is the most common currently used RNN architecture that you're using. So often when you nowadays speak about an RNN network, you mean concretely an LSTM implementation. So the idea is the same thing. So you have some hidden state, you have an input, you always do the same processing at each time step, but we'll see that you try to do a bit more processing in there. You have two types of hidden states, the A and the cell state. And then one is important, you include some type of gating mechanism. And that is maybe very interesting, because this gating mechanism is not only used in RNNs, but in generally, the idea is that you have one input which tries to control the information flow and decides how much information should be put through the gate, or if it should be more closed. So if you can transfer knowledge between that or not. So you have now this extra architecture which tries to control a bit the information flow. And in this case, for example, you have the reading, the forgot, and the output gate. So the idea is, at each time step, we are controlling whether we want to get input at this time step. If there is just junk at this time step, and we might want to ignore it, or if these are important information, we should store them. Furthermore, you can have something like a forget gate, which tells you, oh, everything what happened before, it might no longer be important, maybe because you're now starting a new article. So you might remove some of the information, and you can control the forget gate. And similarly, also the output gate, which allows you to output some of the specific information. So how does it work in detail? So this is, again, our standard recurrent neural network. We have our input at time t, we have our previous hidden state, and based on that, we are inputting, generating the output. The idea in the LSTM now is that we have an additional memory cell. And for this memory cell, the idea is that we can store at some point information in there. We can retrieve information at some point there. And we can also say, oh, now remove all the information you have. We see like maybe a good example of this is also we see that this is really happening. Imagine you want to process text and someone want to mark if something is in quotation marks. So in this, you would have the reading gate at some point mark, okay, if there's a quotation mark, now we are inside a quotation mark. So you write something in your cell state. Then you stay in there. And then once you get the next quotation mark, you tell the model, oh, now you should forget, and you remove information from that. How is that implemented? So for example, first of all, we have this additional cell state, C, which is also at each time step has a different value. And now based on these two states, we can try to like implement our application, implication. So when to read from it, when to write to it, and when to forget things. So the first thing is we want to forget at some time step. So at some time step, we have information in our cell state CT, and now we want to somehow forget it. How does it get? So the one question is, of course, first, on what base? When do we know that we should forget something? And it is implemented that you decide whether you forget information from your cell state or not based on your current input, xt, and based on your hidden state, ht minus 1. So based on these two information, where we are currently and what is new input, we decide should we now forget things or not. How can we implement that? I mean, how to combine these information is just another feed-forward neural network, and you see that. So you take some weight matrix fx and multiply it with x, and you add to it some weight matrix fh and multiply it with ht minus I. Then you have some bias, and that is. So mainly is like you concatenate xt and ht minus 1, you multiply it with the weights, and that will get you this the decision whether you should forget or not. Now there is one important thing. How can we like somehow make things forget or not? And if you think about it mathematically, there is like a very easy way if you multiply things. So if you multiply things with around 0, the result will be 0 and you have forgotten it. If it's around 1, mainly everything stays the same. So if you multiply something with 1, it's just the same one. So you can think of the scaling mechanism exactly with this thing. So you multiply your cell state C here, you see, with either a value 0 or 1. And whether it's 0 or 1 is decided based on that. So of course, in order to have it like exactly 0 and 1, we would use the signum function. Any idea why we're not using the signum function? So which is like 0 if the input is negative and 1 if the input is positive. Yes? That's exactly, the second part is important, the gradient descent. So if you have here the function which is here always 0 and here is always 1, what about your gradients? What is the gradient of this function? So you have a function which is 0 if the input value is negative and 1 if the input value is positive. Yes? It has a gradient, but exactly. So the gradient is 0 for all position except 0, and at the position 0, it's not defined. If we're now thinking of backpropagations, that doesn't work. So if it's 0, your backpropagating path will always multiplied by 0, so you're not learning anything. And even if it's null, it's even crashing because it's not defined at all. So for learning, we need a more smooth function in order to learn that. And that is exactly the sigmoid function. So you can call it like a smoothed version of the sigmoid function. So with this, we are now able, and still we are not always multiplying with 0 and 1, but somehow we are at least like near that. And so then you can learn when you should ignore and when you should put things in there. So it's really, you just take your both states, ht and xt, you multiply it with some weights to the sigmoid function, and then we'll see this one will be multiplied with our current cell state. And then we, of course, also want to write something in the cell state. So at each time, then we want to decide whether we write something in there or not. And if we want to write, there's two questions. First of all, do we want to write or do we not want to write? And if we decide we want to write something, we also should somehow know what we want to write. And for these two questions, it's again the same thing. This should be depending on our current input xt, and it should be depending on our previous hidden state. So this is nice. So we can do mainly exactly the same. So we have our input gate, whether we want to input something, and you see it's the same function that we had before for the forget gate. The only thing, of course, we have other weights. So it might be that we want to forget and not write input, or we want to do both. So that should be independent. Then we have to decide what is our candidate content. So what do we want to write in? First of all, it's the same function. The important thing is now we don't need to have the same type of activation function, but then typically it's better to use, for example, the Tangis Hyperbolicus activation function. And now we can easily calculate our new cell state. Here's a formula. Up there is the drawing. It's exactly the same. So it is, we multiply our forget gate with the old content. So the forget gate decides whether we should keep it or we should remove it. If the forget gate says 0, here we have the value 0. If the forget gate says 1, we have the value 1. Of course, you can view this also as vectors. That means for each of the individual dimensions, you decide which ones you keep and which ones you remove. And then you have the input gate to write something. This gate decides whether to write, and this then decides what to write. So if this is 0, we are not writing in anything. If it's more around 1, we are writing it. And writing means we just add up the two values. So what was there before and what is there new, we just put it above each other. So we have then our new cell state CT, which is depending on what was there before and what we write in there. But the important thing is it's like not uncontrolled, so we're just not combining them, but we have this additional gating mechanism, which allows us to, based on the current input, so semantically based on what is there, to decide whether we want to write into there or we are not, or we don't want to write into it. Once you have written, of course, then the next thing is we also have to at some point want to get information out of there again. And therefore we have the output gate. So the output gate now decides whether we want to extract information from the output state or not. And so what we're just doing is we are multiplying the output gate, which is again exactly the same based on the input and the output, and then like an activation function from our cell state. So we are multiplying the output gate with our previously hidden state. Interestingly, when you think now about HT, what do you see? HT and HT minus 1, if you look at that. Is there a direct influence? Like is HT directly transformed into HT? HT minus 1 directly transformed into HT? Yes? Yes, so I mean, HT is only there to control what is written into the cell state and whether you write something, but it's not here. You see the new HT only depends really on the cell state. Of course, the cell state depends again on the HT, but the information flow is always via the cell state. And then you have this full formula up there, or the graph. It looks maybe a bit complicated, but if you look at it like step by step, it's really nice. You see exactly the 3 gates. So first the forget gate, then you have here the write gate, and then here the output gate. And this is all the information that you are outputting there. And with this, you can now store for in the cell state, you can store for very long time information and retrieve them at different positions. So this is, of course, very helpful so that you can really have dedicated units which look at different parts and so on. So yeah, so the important thing is you have to like force things to calculate the 3 gates, and then you have to also calculate the candidate content. So if I want to write something with my right gate, what do I want to write? And these 4 are calculated and then put into there and used. So if you look at this more from the gradient flow, you see a bit how the gradients flow. On the C, the gradients can really easily flow from next step to that. Just something is added and something is multiplied, so the gradient can very good flow. While you see from the H, you get a new gradient into the CT in there. Yes? Very good question. Has anybody an idea about that already? So what you have to consider there is we had to make this smoothed version of your gating, yeah? So we are calling it a gate, you go either in or not. But to be honest, we had to make it smooth. So like in each time step, something is always written. It's more like how much you write. So that's why you always have to calculate it. So yeah, it's good to visualize these things as a gating, but since we need to train it, we can't do discrete decisions, so in or out. So, but we have to do a bit more smooth. It's important that they are non-linear so that you can do this type of gating, but you do a bit, and therefore you always have to do that and calculate the content. And I mean, of course, it might be also if you're doing it on GPU anyway, it's easier. But even if you're not doing that, doing other, you have to calculate it because you're always multiplying it, and the value is never exactly 0. Good. Any more questions to this architecture of the LSTM? Yeah, a bit more examples and maybe a bit of comparison to between TDN and LSTM. So you have in both cases these weights are shared over time. In the TDNN, you could make longer context, or you could have increase your long range depending by increasing the context, but this also increases the number of parameters and of course makes it difficult to learn. So kernel size of 1,000 or so is normally not happening because it's hard to train that. You have a lot of parameters, you often don't have that much context and so on. In contrast, in an RNN, you can flexibly like adapt to the number of context because you always have this hidden state stored. Therefore, you have to deal with this problem of gradient vanishing and exploding while you don't have this type of problem in the types of TDNN and CN. From a complete computational point, there's of course also a very important difference. Here we have the problem that we have to can do, or we have the advantage that we can do everything in parallel, which makes it really fast. So we can do the whole calculation of all of them in parallel, while here we have to do the sequential computation. So you have to do step by step in order to calculate that. You cannot do everything in parallel. There's also one version or one view of that that's a bit more positive for the RNN, and we'll come to that in 1.5 weeks. If you think about memory. I mean, here you always have to store somehow everything in there if you want to do it parallel. Here you can just do nicely one after one, so you don't have to store the full sequence. Furthermore, there is tricks where you can try to parallelize some part here. And that's why this more like RNN structure is getting nowadays a bit more famous again. It's nowadays called state space models, and we'll do that next week. Yes. Yeah, one more implementation thing about RNN is, well, yeah, sometimes it's really like getting complicated that you have very, very, very long sequences, and then the calculation gets very inefficient. So you have to store all the gradients when doing the calculation. So sometimes there is also this called truncation or truncated backpropagation, so that you're not backpropagating everything for the whole, but you're truncating your sequence and only backpropagating for some time. So you can divide in the middle here. You do the forward pass normally, but you then do on the backward pass only like some part, and you stop your backward, for example, here, and only have the backward flow in there. That, of course, comes with a cost, because it means you cannot learn like dependencies that are very far apart from each other. But you have also the advantage that, yeah, it's better to learn. And sometimes, of course, it's the case that you can theoretically learn, but in practical, it's very hard to extract this information, and you'll anyway not doing that. Good. And then, yeah, we want to close this part about the RNN with some examples of what you can do with this type of structure. So here, for example, it's about like generating things with RNN. So here, generating handwriting. So you see that you can really generate text which looks, or images which looks like handwritten text. And so especially for generation, that can be very helpful. Also, like first models on text generation were based on RNN. Here, like trying to generate text from Shakespeare. This is a bit the last part about the interpretation, which of course gets also more and more interesting. So can you somehow interpret what the neural network does? And what you're trying there, and or some work try to do there, look into the different cells. So especially with RNN, that is now the cells like the CT. So the CT is a vector again, so our cell state, and you can look at the individual ones and try to identify, are they doing anything? Are they active at a special point? And you see here the visualization. So -1 is red and 1 is blue. And mostly, of course, they are not really easy to understand. However, there's sometimes, if you go through them, there's quite nice things you can see. For example, for text, you have here something more like a counter. So it's getting higher and higher. So it's like somehow trying to count where you are, what you're at. Of course, if you think about a sequence, it's somehow important to know whether you're more at the beginning or at the end of the sequence. So you see that there is some part of your hidden state tries to analyze where are you. Here is the one with a example where you have it about identifying where quotation marks or marking quotation marks. You see the state flips at a quotation mark, and there flips again at another quotation mark. So yeah, if you train these on text, you at least can, for some of them, you sometimes can interpret them. If you train them for more program code, they found that some are, for example, for indicating the if statement. So you always have here the if condition activated, or other ones which try to be like activated here on the comments in the code. Good. So for summary of last lecture and the beginning of today, what you should remember is, or what is really important, to have these two type of architectures. And now both about the differences and the similarities. They are both are there to like transfer one sequence of hidden state into another sequence of hidden state. The lengths of the sequences can be different, but typically you have exactly the same number in input and output. And this can be done with recurrent neural networks, with LSTMs, or with CNNs. And especially we have then also how to train them, backpropagations through time. And we again saw like the similarity between backpropagations through time and the training of a CNN. And this is normally the idea that you share the weights so that you're replicating your weight several times and thereby train the model in this way. Before we are then going for the next type of architecture, do you have any more questions to that? Yes? I mean, nowadays they are often replaced by the next one, the self-attention. What they were used a lot for text, and partly they're still used for text in the way that in a generation task, so in an analyze task where you have the full input available, their transformer is really a lot faster and better. But if you want to be fast on generation, where you can't process your whole input at once, maybe you remember this, where we discussed models where you have the autoregressive model, which generates one input by another, then often still LSTMs are a very fast solution. And we'll see that, yeah, one new idea where people think about what can we do instead of transformer, the state space models, they are very strong related to this type. Okay. 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 So, yeah, and then today, as the next type of architecture we want to look at is self-attention, which is the main, yeah, component of transformer neural networks. And you might have, yeah, known that this is currently the most commonly used technique in at least all text and speech processing, but also there are things like visual transformer, which are very successful used in vision application. So somehow this is like the core component of, yeah, most of the current AI systems or large language models that you're seeing there. If we're thinking about what we just learned, is that we have this RNN, which represents your input, your sequence based on the input and the representation of the previous one, and we do the same thing at each position. So the nice thing is we have a global history. We at each time step know everything we just learned. However, there's also, of course, a challenge, or there's something which comes with it, and that means we have to store all our history in like one fixed state. So we only have this one fixed state where we have to store everything that we know about our sequence. And if you now think of yeah, very long documents, so think about you want to do a document summarization or summarization of a book, then it might at some point be difficult to store everything in this one like hidden unit. So of course you can make things larger, but it's always you have to predefine. So you have to define, oh, my history is my vector is 1,000 dimensional, 8,000 dimensional, anything, but you have to predefine it. And the more and more you store it, at some point you will typically see that things are getting written over it. So you write things in the same hidden state. So if you think about that, if you again, now we're luckily just had the LSTM, so you have this writing back there, and you do the writing back by taking the old vector, adding the new vector. And then if you have two information and there's no new dimensions where you store things, you might just add two things up to each other. And it might a bit look like that you at the end, you can no longer disambiguate what was really written in there, but just because just everything is scrambled upon each other and you cannot distinguish it anymore. So this is, of course, a bit a challenge because you have these types of fixed representation. Also, I mean, we address the problem, but long-range dependencies are still a challenge. I mean, we are getting a lot better with LSTMs, but still we need to like propagate everything till the end. So if you analyze it, it's very good at learning small dependencies, but for very far away, that is still often an open challenge and can't be done perfectly. Finally, the computation is really intensive and it depends on the sequence length. So you cannot do like parallel processing, but you have to process one after each other. That's normally fine if you generate something, because then you don't have all your input anyway at one time. So you only read in once or like output once. But if you think about reading text, you have a full text. And then, of course, it might not be efficiency if you process one word by one and do individual computations for each. But it would be nicer if you can just generally do like process all in parallel and do that in parallel. And that is maybe one also important thing which can't be highlighted enough when you think about self-attention. So this was one of the first ones where there's now a layer which was somehow specifically designed with knowing already what are the current limitations of computers and graphic cards. So if you think of LSTMs, they were developed by Schmidt, who were in the 1990s. There was no one really calculating on GPUs. Self-attention and transformer got really famous with this attention is all you need paper. That was 2017, I think. So there, everybody was using GPUs. So it's really already in some way designed in a way that is like optimal also for computation. And that is important, as I mentioned before in the lecture on GPUs. So nowadays, if you want to really build strong systems, they need to do so much computation so that it's only possible to good if it somehow matches what you can really do. Because of course you can build a very small, nice model which is working good, but it might be that this doesn't really scale well. So what is the idea of self-attention? The idea is when we calculate our new hidden state, here, for example, at the last position, we are no longer want to just take what we had previously or what like a fixed context, but the idea is, can we somehow focus on different parts? So can we look at the previous hidden state, what we had, what is important, what is helpful in order to understand the new state, and then take all the ones which are important beforehand and use them to calculate the new one. So the idea is we don't have a fixed one. We are not processing one by one, but the idea is look back and see, oh, what is there important? Take the important bits out of it and summarize them in a new thing. So focus on what is really important beforehand in order to generate that. It's a bit like if you think about you have a task, then you read over the text, you think what is important, note them down, and then all this information you put in here in order to understand that. And then we're doing it each time step. So in each time step, we just try to summarize what was there before, or we'll see also what was there overall in the input, what is important for my, summarize this and use that to generate the new text. So the first question is, of course, how do we summarize in vectors? So we have now many vectors. How can you summarize a lot of vectors into somehow one vector, which is important? Any idea for how to do that? Yes? Yes, a sum is a good idea. So that could be the first. So we could just summarize everything. I mean, if you do sum or average, it's not a big difference. It's like you normalize. So you could just summarize all your hidden states into one and use them. There's one problem with normal summarization. If you do that now, you sum everything, you get here your first state, then you sum again, get here your state, and sum again and get here your state. What will be your result? Yeah, so everything will be same. That's not super helpful. So what we're instead doing is we're doing somehow a weighted sum. And now that is like a bit the challenge, how to determine the weights. And that we'll look in. So the idea is we're doing this summing to summarize everything into one hidden state. So to get our new hidden state here, we're just summing over all the previous ones. But what we're not doing is we're not just doing a normal sum, but we do a weighted sum. So some are more important and some are less important. And of course, now that is a challenge. How do you determine which is important or not? But somehow it's really nicely, again, highlighting to you what is how you focus. So based on your weights in your sum, you focus on different parts. Then you take the one which are most focused and add that one there. So yeah, the question is a bit, how do we define what part is important and what part is not so important? And to do that, you can think of this type of self-attention, also look at it more from what you know from databases and so on. There you also have to somehow look what is important for your query and find that. Exactly like that, you can view that. So how to create a relevant summary, you can look at this from more the data science perspective. So the idea, and that is very good to remember this time, because we'll see a lot of terms which will occur and which are then easy to understand. So what are you doing in a database? So if you want to do a question on the database, you first have a query. So you want to know some information. You want to query the database with your current query. And this type of query is also what we're using here. We'll talk about of queries. The query is like the element that we want to use in order to get something from the database. Then if you remember database, when you have in the database, you have a lot of keys. So you compare your query to the keys and then find the most similar key. I mean, or yeah, the exact one. But here we'll do all the things a bit more smooth. So somehow, but we want to find the keys which are relevant to your query. And then you might want to retrieve the associated values which are associated with its key. So maybe this is a bit more abstract. So think about it more or less like in the example. So what you here have is a menu from some restaurant. You have the food they have, and they have the prices. So you can think of the key as of your food, and the value is the prices. And now you want to know how expensive is a burger. What you're doing is your query is then burger. And now in order to get how expensive a burger is that you compare your query with your keys and find the one which is best matching. And this will give you then your result. So you'll get something like 10. If you're doing this way, if you think a bit what we talked about in LSTM, does anybody already see a bit of a challenge? You select now this one element which is most relevant and extract that. You think about learning in a neural network. Yes? Yeah, so you have somehow a hard decision, like a hard decision, like a discrete decision. There is some tricks on doing that, but in general, this is often very, very challenging. So doing like hard decision, you always prefer, if you want to do some learning, to have more a continuous thing. Than learning just works better than in discrete decisions. Yes? That's exactly what we're doing. So we're not exacting the best one, but what we are doing is we are calculating similarity between our query and our key. So the similarity could be something like 0.5, 0, 0.5, and 0. Maybe this is also not completely 0, but you're rounding it. So we'll see. You can get in. But the thing is, you're not directly finding the most relevant one. But what you're doing is you're calculating the similarity between your query and all your keys, and then you get a similarity values here. So these are all the similarities you have between your query and keys. And then, so how do you get the price? And then you exactly do that. You do the weighted sum. So you multiply your similarity with the values that you have. So here would be 0.5 times 12 plus 0.5 times 10. And so you get 11, which is somehow a good results for that. And that is how you implement this in the self-attention. So you have your query. We have to see what in sequence processing is our query. Then you're comparing the query to all the keys that you have. You're calculating a similarity, and then you're multiplying your similarities with your values to get the full one. And you already can see in the small examples some important like dimensions. So for example, you can have one query. If you have one query, you can have the number of keys doesn't really matter. You can have as many keys as you want. In the end, you have here again one value. So if you're no longer like defining here, oh, I need to have 3 or so from your parameterization, that's all the same. There's only one restriction. I mean, there's one important restriction here. If you're doing that, so comparing query to keys, getting the similarities, multiplying with the values, the weighted sum to get that. So your input is one-dimensional, your output is one-dimensional. You have some number of keys and some number of values. Is there some restriction that you should think of? Yes? That we will come. I mean, that is nothing we have to do. I mean, in your weighted sum, you can do it or you cannot do it. We'll see in the in self-attention that is typically done, but that is more for computational reasons. The advantage if it's sum up to 1, you again don't have like some time of exploding or vanishing problem. You can imagine if all similarities are nearly 0, your result will be 0. That might not be very good. So it's more for stability of your training. But is there anything about the number of query of keys and values that you should consider? How many keys, how many values can you have? Any restrictions on that? Can I have 7 keys and 5 values or something like that? Yes? Yes, so that's important. So we need to have the same number of keys and values. The absolute number is not important, but the number here needs to be the same in order to like assure that we have really like a valid way of doing this type of calculation. Okay, so now we have the high-level idea on how to do self-attention. But I could imagine you might not directly see how to do that now on a sequence. So what we have is we have a sequence of vectors and now want to generate a new sequence of vectors so that we have the same type of input output as we have in RNN. We have a sequence of input, sequence of output, the same thing we want to do here. So how does it work? And here is like the first, we start with a visual version of that. We'll then also go into the individual formulas of how to calculate. So how does it work? So we have our input sequence 1, 2, 3, 4, 5. And then we first can use, we said we have one query. So let's start. We have one query. The query could be the first hidden state, it's the first input. So the idea is we want to know which information are now important to understand this first input token. In order to do that, the first one is now our query. That's the yellow one. And we are comparing the query to all the keys. What are the keys? Which information could be important here? Could be all the other important information from the input. So what we're doing is we're comparing the query of the first hidden state with the keys of all our hidden states. And then we get here the similarity of the first token to all the tokens in the sequence to itself That's the first one. So how important is it itself to understand itself and to all the others? We're calculating the similarities, and then we're getting in orange this type of similarities in order to understand them. And then we're doing there a normalization. So these orange ones, we normalize that the sum is 1 and that they're all between 0 and 1, so that this is a probability distribution. This is there that we can have a more efficient training because we are not having the problem of exploding gradients or things like that. If we have that, we then have to do the second step, where the second step is now to calculate the different things. So we can do now the weight times our values at each position, and then gives us glue the new hidden state. So with this now, we have calculated our new hidden state for the first position. We have as input the 4 hidden states. We took the first one as a query, and that will give us then here the first hidden state. With this weights, so this orange one allow us now to focus on the different hidden states. So it can say that now, oh, word 3 is most important to understand the first one, or word 4. And this is not really depending on the position. So, I mean, a weighted sum, the nice thing is information can really flow from the beginning to the end to everywhere very fast, like in O of 1. So it's not that they have to first transport all the way through it, but if the last hidden state is very important for the first one, we do the direct comparison, have a high value there, and the information can directly flow. So we're not having the problem that information need to pass through the whole sequence or something like. You also have seen that we have these 3 types of, so our input is transformed into a query, into the keys, and into the values. Well, see, that is just a linear transformation. And the idea is that you want to, like, if you have one input, there might be different information which are important for what is a query of this input token, what is the key of this input token, and what is the value. So you're learning individual transformation, which tell you, based on this input, how important is it to do one of these things. And then, I mean, now we only have getting one hidden state. Of course, we need more hidden state. We want to have one hidden state for all our input token. The nice thing is we can now do exactly the same thing at each position. So what we now can do is we just take a different query. So this time, the query is based on this one. So we take this one, transform it into a query, and then do exactly the same calculation. So we take now the query based on the second hidden state, compare it to all our keys, and get how important all the states are in order to understand the second token. And there we again get different similarities. So of course, these values are now different, but we can in that way calculate it the same thing. And then again, do the weighted sum and get then our second hidden state. Yes? I mean, the query is currently your current word yet. So it's like if you have these as words, you somehow see how important are the other words in order to understand this word. So you use this word to query the other words and ask them how important are they in order to understand myself. Yeah, that we will see now in the next step. So how can we generate this type of query, query key and value? And this is this. So our input is a sequence of vectors. So we have our input sequence is n vectors, with each one has a dimension of big n, of small n. So you have here xn. So you have big n vectors, and each one has a dimension of small n. So here is a vector, the round blue one here, here, and here. And then in transformer, the first thing is that you calculate now the query key and value. And these are 3 transformations. So W matrix n times H which what they are doing is you apply this same transformation at each of the positions. So out of I of the hidden vector, you make now a query, you make a key, and you make a value. Out of like, you make a query, a key, a value. Out of you make a query, key, value. And out of movie, you also make a query, key, value. And that is just by taking your input, multiplying it with the matching weight matrix, and then to get query, key, and values for each of them. The interesting thing is these are all the parameters you have in a self-attention layer. So now we are doing a lot of calculation afterwards, but these are the only things you really can change, the only things you can really learn. So all you have to learn is what is the right query, what is the right key, and so on to do things. Yeah, so you cannot, like, how to do the comparison and so on. At least in a lot of current models, we see there are some where you could do that, but currently you just use there for calculation. So you have to learn mappings that somehow your query here is a very meaningful representation. Your key is a meaningful representation, and also that your value is a meaningful representation. Yes? No, it would be just, I mean, the query layer would be just, I is already a embedding typically, so a vector of like 100 dimensions, and the query vector is just another vector which you learn from this one. So you have to learn how to transfer them in order to get a meaningful. Not that easy. I mean, what you can somehow interpret is later, or what people at least try to interpret is the weights of your attention. So how strong, in order to understand one, how strong is it connected to the previous ones? No, I will come to that, what the attention is. Was there another question? So then the next step is to calculating this type of first of energy function, which then describes your attention. So somehow you want to describe how strongly are two words connected, and you have these two-way connection. So on the one hand, a query from one word, and then the key from the other. And of course, that is not symmetrically, because you learn different mappings for query and key. So it can be that one word is important to understand that word, but the first word is not important to understand the other one, because you're learning different mappings for the query and key. So that means like EIJ is not the same as EJI. And this is exactly what we said before. So you're just calculating the similarity between this and this, this and this, and this and that. So in order to get one new hidden state, you have to do linear combination with all of them. You see in total, you really have to compare all with all. So you have somehow a quadratic matrix, because you have to compare this one with all, this one with all, this one with all, and this one with all. So all with all. So you have in the end this attention matrix, which says like how important each input is for each other input. And now the question is, how do you calculate this similarity? So how do you say how similar two vectors are for each other in order to understand it? Justin, any ideas what you could do? You have one vector QE and the other one is KJ. How do you say now how similar they are? Yes? That is one, or even the most common one. So the scale dot product. So what you do is you take query and key and just multiply it. So you can also do that in this writing if you do it for the whole sequence. So what you have is you have your keys, all the keys. Then you have the sequence times key. So that is how big your key is. You see, query and key have to have the same dimension then. And this time, otherwise you cannot compare. And then as output, you get the similarity, which has the length of the sequence. So Q is one single vector. Then you have here a matrix, which is like all the keys, which has sequence length times key dimension. You multiply them according to the key dimension, and you get the similarity, which is the length of the sequence. You're doing there often or typically some normalization based on your dimensions. So if you have like each key has a dimension of 1000, you would have you normalize it by 10, because that is typically there for stabilizing your training. But basically, this is just a dot product which you can do, and you scale it just a bit by this key factor. But of course, there's more things you can do. So you could think of that. Maybe it would be important to have more weights in there, like to learn something. You can also have add a weight matrix in between to learn how to combine these two. So you multiply your query with a weight and then the resulting one again with your keys. Then you have additional parameters, and the idea is you try to learn how to compare them and use them. Any idea why it might be the first one might be more commonly used? Yes? The less computation is one reason, but I mean, yeah, less parameters are partly good, but partly they are also bad. I mean, you want to learn something, so you need parameters. So why is this maybe unnecessary to learn this type of parameter? I mean, you mainly can learn this one also, but just learning it within your Q1 already. So you can at least a lot of these, instead of learning a separate W here, you can just learn a different metric from your Q. And since your Q is already learned, you have that then in there directly. The other one, which was done off at least at the beginning, where this query key value weren't learned beforehand, is that you of course can also just take an MLP again to learn this type of weights. So you do have just a sigmoid function, and then you have here mainly a neural network based on the query and the key, and you're learning how important the query and the key are for each other. Because here you have then a lot of parameters which you can learn, but you also have the disadvantage that you need a lot of more computation. And because currently there's just so many like of these attention layers in standard transformer-based models, that typically you won't have their very complicated calculation, then it's better to have a relatively simple calculation and therefore stack more layers or so in order to have then in this way a more complicated type of calculation in there. So this is some of the first step. Then we need to do the second step. This is the normalization. So where we normalize our similarities here in order to have a probability distribution. How we can do that, we learned already for other things. We can just apply our softmax activation function on that, and thereby ensure that this one is like a probability distribution. Does anybody remember how the softmax was defined? So we just take e to the power of each of the values and then divide them by the sum of e to the power of all of them. Thereby we ensure that first of all of them are positive, and secondly, we ensure that they are like a probability distribution. And with this, we can then do the final step where we take the sequence here of our attention, like of our attention values, so how important each of them, and we multiply them with our values, where each value is multiplied with the matching value. And then we are getting our final like output here, the orange one. So since we're using the key the query from the second state, we will also get the result from the second. And then we can do then for all of them, and then we'll get the same sequence of hidden states. So our input here is a sequence of hidden state with length big N, and our output will be also, because each input once was a query, so it generated also one new hidden state. So you see from that one, you can just plug and play CNN, RNN, and self-attention. You always have a sequence of hidden states as input and generate a sequence of outputs. Of course, in some cases, the one or the other might make sense. They have different properties, but from the architecture first, it's always a transformation from a variable, say, length sequence into a sequence of exactly the same length. Altogether, it's exactly this type of formula. You take the softmax of a comparison between the query and the keys, and then multiply the softmax with your values. And then you have the overall type of result in there. And this is what is done in self-attention, and yeah, which is currently like used in most sequence processing architectures that you have in order to generate a new one. And the interesting thing is now at each position, you have information about the whole sequence. So that's a big difference to RNN, for example, where we said we only have information about the previous one. Here you have always information about all the others. They fly bidirectional here, and they directly go without like the problem that it might take too long to go from one direction to the other, and so on. Yes? I mean, this is in this type of notation, you explicitly say across which dimension you do this type of multiplication. So here you do the multiplication across the key. That means your result has a dimension sequence. And here you do the one across sequence. This has no sequence. This has sequence times if valid, so that you can then again get a value. Well, now here it's like a vector, two vector multiplications, where this one, I mean, yeah, it's a, yeah, because you have a lot of vectors and you do it, it will be a matrix multiplication, but it's, the question is across which dimension you're doing it. Any more things unclear on this type of self-attention? Hope that doesn't mean that you all. We'll look into more details on that, but really the important stuff is the 3 steps we have here. And yeah, the nice thing, oh, maybe, yeah, that we didn't, I said at the beginning, the nice thing is about the computation. And here you nicely see now, there is no dependency within the layer. So everything is based on your input. And that's why you can, all the computation you can do in parallel. So it's really nicely parallel on GPUs, because how you calculate this type of attention, you can do that all in parallel for all the inputs. So if the input is completely available, you can process all inputs in parallel and don't have to wait for intermediate representations in between. We have here already the name like self-attention. So of course, then there should be a bit of other attention too. And this is especially important for, yeah, for example, encoder-decoder models where you want to attend to other parts. And that is, the idea is if you have like a model where there's 2 sequences. So for example, in translation, you have that you have somehow an input sequence, and then you have an output sequence. And the one sequence wants to extract information from the other sequence. You can do what is cross attention. The idea is very, very similar. The only difference is now that your query comes from another model, or like another part of your model than the keys and the values. So you have here the sequence, I like the movie, and they provide the query and the keys, but now you're not attending to yourself. for self-attention. Say you attend to yourself, to your home sequence, but you have another sequence which tries to to attend to this sequence to extract the most important information. So what you're doing, you're taking this query here, you're comparing it to all the keys of your sequence, getting the similarity, then you're taking the values from this one, multiplying it with the query, and that gives you the summary. So thereby, you can not only like extract information from yourself, but you can use the same mechanism to have one hidden state and extract informations from another hidden state. That's, for example, in generation, like encoder-decoder models, where you have one model which stores the input, and then you have another model which generates the output. You're always taking this, attending to your hidden state here to get the most important information out. All the calculation is the same. The only thing is you have the query, there is the model that does the search, and you have the key and value that have the data storage. And of course, the key and values, they need to be, again, the same lengths, because they are used to calculate the similarity and then use the similarity as a weighted sum for the values. So you can also formalize that. So you have one key now, you have a sequence of keys, you have a sequence of values, and then you multiply your query with your key and then get your final value. So the calculation is all the same. The only thing is that you now have also the ability to, like with one model, attach to another model and so on. You see here one thing, of course, you have to make sure if you use the scalar dot product is here, the dimension of the query and the key has to be the same. That you can normally easily achieve. If it's not by default the same, then you can just achieve this by using a linear transformation, and then you can like normally do any type of change in your dimension. Good. So this is the basic transformer. Now we'll come to like one typical extension to that, which is the multi-head attention. So the idea is, I mean, now we have the ability to focus on different parts. But sometimes it might be that in order to understand something, it's good to focus on this part and also to focus on something else. So if you think about, I like the movie very much. In order to understand much, it's important to focus once on very, because it's like saying how strong, and it's important to do it on like, because it's saying that but they are somehow having very different meanings. So that you just average over very and like might not be the best idea. So the idea, can we also do something else? And as the multi-head attention says, the idea is, oh, maybe it makes sense we're not generating one summary, but we let two independent systems both generate a summary and then like combine them again. And then the one can more focus on one part and the other can focus more on the other part. And we can learn both systems, and we can learn them that they do maybe different types of tasks. And this is, yeah, quite straightforward as we did it. So the only thing we're doing is, if we have a d-dimensional hidden state here, where we can interpret them is as two d-dimensional hidden states. So we're saying our query, if it was before a 100-dimensional hidden state, in reality, this is like the first 50 dimensions are one hidden state, and the second 50 dimensions are the other hidden state. You can do the same for the query. You can do the same for the value. So you mainly have now two pairs of query key values, and you achieve this by using just like interpreting your linear, transformation in this way. And then you can do the calculation we had before. You can just make them independent of each other. So you first can calculate your hidden states, your new one, your self-attention, only based on the lower ones. So here you have, the lower query key value pairs, and based on that one, you calculate your new hidden states. That's your one type of attention. And you're comparing now this query to this, and this key, and you get a similarity telling you for this type of submodule, how important are the other words for that. So you can, quite straightforward in this way, understand that maybe in this time you see it's mainly looking at itself, that's very dark black, and then maybe a bit on like and so on. Now we have the other pair, so we can do exactly the same thing with the other pair and also calculate based on the upper ones our similarity. And maybe now these are different values. So I mean, we learned them. So the attention can be completely different. So now we can see, oh, for this type of information, it's more important to look here than there or so. These are two just, we do exactly the same calculation, but you're no longer saying that you have one fixed attention, but once your attention is based on the lower ones and once it's based on the upper ones. Now you have two results. And what you then can do is you can just merge them. So you can just merge your two orange results here to get your new hidden state. What you, of course, want to somehow do for a fair comparison is to have the same number of parameters, but by just like having here your hidden space, you have nothing changed. So you learned, I mean, we said the only parameters that we have is the linear transformations down here, and they were all the same. So it's exactly the same number of parameters. We just did a different type of calculation. And that is what is typically done nowadays. So most models have, for example, typically is like 8 different heads, which means you split your hidden state not only into 2, but into 8 different here, and then do this comparison 8 times to have the ability to focus always on different parts there. And so that is what people refer as the multi-head attention, and enables us to not like focus on a single type of information, but to focus on very different types of information. Any questions about multi-head attention? Yes? I mean, the idea is that maybe sometimes the word like is important, and to understand other parts of the concept, the word movie is more important. And maybe just averaging is not the best. So what you can do is here, in order to understand this part of your content, like which is the lower dimensions, it's more important to look here, while in order to understand this one, it's more important to look in the upper one. Yes, you can view it like that. Similar is now difficult to define. I mean, normally you stack several self-attention layer on top of each other. So you still have that. Here, this is within one layer, but of course you can also interpret it as a bit more like parallel layers, which do some parallel type processing, which you then like merge again. Therefore it's good. So we're have understood the basic concepts of self-attention, or at least I've shown it. I hope it was understandable. But there's one important thing which we haven't considered, and which is essential in order to like really do this type of computation. So when we're looking at the hidden states, if we are having an RNN, your hidden states always depends on the previous hidden state and on all the previous ones. If you have self-attention, it's a bit different. It's like the new hidden state always depend on all the other inputs that we have, or we have no dependency between the hidden states itself. So a hidden state only depends on the previous ones, not on the others. So it's a bit more similar to CNN in that way. That's also a big advantage, because that means here we can't do parallel processing, while here we can nicely do parallel processing. But if you think about this type of sentence, Mary kills John, there is one problem with this type of processing, so that the hidden state is the weighted sum of all the other hidden states. Anybody already know it or see it? It's a bit far, I agree. And maybe somebody has what a problem of, I mean, mainly what we're doing here is a weighted sum. What is a problem of a weighted sum, which might be, especially if you think about text, might not be the best way to do it. Yes? Yes, exactly. So it's not, the hidden states are the same. They are in a different order. But exactly as you say, if you now have John kills Mary in here, the hidden state associated to John here and here would be exactly the same. So they would be in a different order, but Mary and Mary would have the same hidden state. Kills would be and John. While here we have a different thing. If you have an R and N, it always depends on your previous hidden state and your input. So this first hidden state is completely different than anything which happened here, because it was never that you have here like the start hidden state and John as input. And kills has a different representation in both of them. So here we have positional information always in there. While here, I mean, somehow there is still position in there because the first hidden state is different. But the problem is the first hidden state here is exactly the same as the third hidden state here. So, which means if you just take your hidden states at the end, you have something like a bag of word representation. So where the hidden state doesn't really depend on how the sequence is. And that is, of course, very bad for sequence processing, because the order of the sequence is essential. So, I mean, Mary kills John has a very different meaning than John kills Mary. And you shouldn't have, I mean, somehow you should have this type of interpretation in there. Otherwise, I mean, we could just average everything and just do MLP on top of that, and that's it. So we need some type of processing to disambiguate these two meanings. Because if we are, just processing them the same way, then a lot of text understanding is not possible, because it heavily depends on where things are. If you think about it, for understanding very, it's important to know what comes next, and it's not only important which other words happen in there. Any question, or is this problem clear? And especially, it's important to understand why this problem arises, so that we are, like in all our calculation we did here, we did not consider the position. So what we're doing is we are comparing, but there we're ignoring the position. We just take the vectors. Then we get the weight. We just do weight times value that's for the same position. And then we do a sum. The sum also ignores the position. So there is no thing where we have any like encoding of the position in there. So what to do? And the interesting thing in transformer is the idea is not, oh, we have to solve it in transformer. We have to like somehow adapt our architecture and change it that it's like positional aware. At least that's not the basic idea. The first idea is, okay, if we can't handle it, let's try to handle it before. And that is what is known as a positional encoding. And the idea is, if we can't do it in our network, just encode the information before. And if Mary kills John and John kills Mary is already a different type of representation, then of course this information doesn't get lost and we keep it. So the idea is, if our input not only encodes that this is the word Mary, but that this is the word Mary at position 1, and this is the word killed at position 2, and this is the word John at position 3, and here we have the same but with different positions. Now, if our hidden representations here are already different, and here are different, and for Mary are different, then of course, if our input is different, then also our output is different, and we no longer have this type of one-to-one mapping. So we don't have to consider position somehow in this calculation. If it's stored without our input vector, and that is different for different positions, then we can do the calculation independently because we have encoded it. And in our vector, it's already encoded that this is position 2 and 3. And then the similarity will be different, whether it's like the John and Mary comparison between position 1 and 3 or between 3 and 1. This idea a bit clear, or any questions to the motivation for that? Good. So we have an idea. If we have an idea, it's a good first step, but the second step is we need to somehow also implement and describe. And therefore, there's different ways of doing it. So let's start again. How do we put in words or any discrete tokens? We said for this type of discrete representations, what we're typically having is this one hot representation. So we have an array where, like, at one position we have a 1, and at all the other positions we have a 0, saying that, okay, this is the word Mary, this is the word kills, and this is the word John. So these are really huge vectors. If you think about, like, you normally limit your vocabulary, but then you're saying like something like, yeah, the number of words is 10,000 or so, then you still have here a vector which is 10,000 dimensional, where at one position there's a 1. And here's a 10,000 dimensional vector where at one position again there's a 1, and so on. So this is your vector. And then the first thing is you're doing word embeddings, which is this linear projection into a lower dimensional space. And this is then a continuous vector saying a bit what is the meaning of the different words. So how can we add now their positional information? The easiest thing is we can not only encode that what the word is, but we can also encode the position. So you can have positional encoding saying, this is position 1, this is position 2, this is position 3. And what you then can do is learn again positional embeddings, which tries to learn a mapping from this to the next one, telling you what is a good positional information. So exactly the same. You just now have for every word not one input, like only the word index, but you also have the positional index telling you at which position this is. Yes? No, I mean, these are two independent types of mapping, so it's not the same. So yeah, it looks here bad, that is true. But of course, I mean, this is one W matrix for the words, and this one should be independently, because of course it doesn't have any influence whether it's like index 0 or position 0. So yeah, that's a very good point. So you have to like just have there two mappings, one from word index to word embedding, and one from positional index to positional embedding. And then you can just combine them. There's different ways. The easiest is you can just concatenate both of them. You can also sum both of them. Why does summing work? I mean, these embeddings are learned. So if you sum them up, they will somehow be learned in a way that it's reasonably and having a good type of fit in there. So in this way now, you see up there, now the Mary has a different type of representation, whether she is at the first position or she is at the third position. And so you have exactly achieved that. However, there is somehow there might be some challenges with it. Does anybody see what could be a disadvantage of this type of positional embeddings? Yes? I mean, this positional, these are two mappings in between. So, I mean, that would be correctly if you would learn an independently mapping for each position. but you learn one mapping. I mean, it's a good point. So it wasn't clear from you, but you learn one mapping for the word. You learn one mapping for the position. And so you can even embed words that position it was never seen, but so it's not exactly the problem, but it's very, very near to the problem. So the problem is it's very related. So you're thinking exactly in the right direction. Just think about like a long sentence where you have a word at position 59 or so. Or 82 or something like that. Yes? Yes, so I mean the long for you have less and less sentences which have more than 80 words. So these embeddings will not be learned very well because you maybe have like 1% of your training data is more than 180 words. So you only in 1% of the training data you have seen this embedding, and then it might not be a very well trained embedding. Because of course it's nice if you want to learn things, it should be like somehow equal distribution. That's the best cannot achieve. But here we really have, I mean, the first word is in every sentence. The second word still in most of them. But if you go to like 82 or even 159, then there will be very few sentences which are that long and where you can even learn that because most sentences will be shorter and this doesn't occur at all. I mean, of course, the other problem is, of course, you also still have to somehow limit that. So you can only learn what you have seen once in training. And if you have a sentence length that is longer than everything you have in training, it's no longer possible because you cannot do this type of thing. Because you have to at least once have learned this type of embedding. Yes? The problem is it's not that easy because even like there's a big difference between 100 and 101 because they are like, it's important whether you have, say, very much or much very. That is complete. So the order is really important. And it's not like that for the long ones, you can somehow ignore it. But something in this direction is what is at least the most commonly applied approach is and that is trigonometric functions. So the idea is these are like they're like if you think about sinus and cosinus, these are there for ever, like they're applied forever. So what you can do is you have for each dimension one function, either sinus or cosinus, and that you have them with different wavelengths. So you might start with a very long wavelength, and then the difference between the positions not that much, but then you get always shorter and shorter. So you see it here. So for the even directions, you have sinus. For the odd dimensions, you have cosinus. And then this is somehow your wavelengths encoded in there. And by this way, now at each position, you're adding a vector to that. The vector is not learned, is somehow fixed, but it's different at each position. So at each position, you're adding something else onto it, and thereby you ensure that your output is different for that. Of course, at some point, if you have, if all your waves are again the same as at the initial one, it at some point can happen that you have the same embedding, but that's typically very far and it works. And yeah, of course, it's also still good to have a lot of sequences seen so that you can handle this type of representation. So if you use this, you can generalize to longer sequences that you've seen. But of course, you see a drop of performance because it's only used that you add this type of positional embeddings and not anything else. But with this, you're not having a learned parameter, but you have somehow a fixed, which makes all of them the difference. By just adding this type of wavelengths to all the positions. So what you're doing is you're taking your one hot representation, you're learning the word embedding, and then you're adding to up it here, this positional information, which is based on the sinus and cosinus values. And then these two added vectors, you get there to get your new hidden representation. Good. Any more questions to this? Yes? I think so. I'm not 100% sure. There is a learned one. There was some, and I think they work quite well for short. I mean, it of course depends a bit on a lot of things. Like there you have more parameters. So you will use the same hidden representation now for the word embeddings here, or do you say this one can have larger word embeddings and so on? So the comparison is not super easy, but I would say in general it's performing similarly. Yes. 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 D is, no, D, sorry, no, I is a position, sorry. I is a position and D is here the dimension index you have of your word. So E is a position in the sequence and D is the position in your word vector. So this is the 0 dimension, first dimension, and so on. And D model is the absolute value that you have. Sorry. Good. Then, yeah, we can continue on this on Tuesday with some more positional embeddings.